Hi, and welcome back to Book Club. Actually, Book Clubs 2 through 5. Dr. Andrew Duggleby. And what I wanted to do was actually thermodynamics, but then realized that thermodynamics is so close and tied in to fluid mechanics. And then honestly, the graduate level fluid mechanics actually has stuff that really should be in undergraduate, and then in the physics program, which is called statistical mechanics, there's really stuff. So, you know what? I just decided there are 4 awesome books, and we're going to cover them in the order that I think makes absolute sense for you, dear reader. And so when you look at just thermodynamics, it's really fluid mechanics and heat transfer and mass transfer. And we're going to use those to solve energy problems, that a car engine, a gas turbine engine, the motion of things with heat and fluid, which is super interesting. But then if you really kind of compact it together with thermofluids, well, it's conservation of mass, conservation of momentum, which then deals with pressure, viscosity, conservation of energy, which will have internal energy, work, heat transfer. So all of this really makes sense to sort of teach together. And, and I talked all of this when I was a professor. I think the biggest thing I realized is that in every undergraduate program I know of, we send our students through, at least 4 courses of mathematics, 2 years, right? It's usually like 3 semesters of calculus and 1 semester of differential equation. And then by the time you're taking a thermodynamics class or a fluids class, you might be in a 5th math class, linear algebra or something like that. But then in these textbooks, they're almost always very, very basic, and they shy away from the math. And they make sure that they might flash you the math, but then they're going to sort of extend it back out into all the algebra that you would be familiar with from high school. And just really realized that mathematics is a language, and we've invested in these students so far. So many of these concepts will actually be really easy to teach if we just keep the language of the mathematics. And then, yes, if you're going to go solve it and it happens to simplify down to some algebra, like great, that really helps solving problems, but it's not the point of it. So it's really, things like integrals and coordinate systems, we shouldn't shy away from that. A lot of these textbooks are redefining it or being too scared. Differential equations, students should be very familiar with differential equations. They've at least seen it once, and then this is our opportunity to show them again how it's all tied into physical phenomena. And then, like I said, linear algebra, most undergraduate programs are going to require some sort of linear algebra. And then, honestly, this thing called Einstein notation, which is where we actually sort of level up our way of handling vectors. It's usually not taught into the graduate curriculum, but boy, it sure makes everything in fluid mechanics and thermodynamics just honestly way easier if you have that tool set using the Einstein notation. That's why he came up with it. It really helps make mathematics just simple. And then you can work with it. It's less obscure than trying to remember all of these weird formulas. Right? It's just like if you took high school physics and you were looking at, distance equals, 1/2 acceleration times square. Like you used to remember these formulas, and then you finally got into calculus-based physics, and you were just like, oh, distance, I just integrate velocity. Like it's that sort of simplicity. So that's what we're going to do. And the 4 books that at least I'm going to kind of, book review on, and also you can find kind of your own. Honestly, all of these topics are all well covered in, honestly, any undergraduate book. But, for at least my, where I'm going to get my high-level thoughts from, it will be Engineering Thermodynamics by Moran and Shaipro, and they've added a couple new authors. Fox and McDonald, kind of a classic and sort of fluid mechanics book. These are the 2 I used to teach with as a professor. Ron Panton makes a fantastic sort of graduate fluid mechanics books. I took it from Dr. Panton. He was a joy. I'll have some funny stories there for you. And then Statistical Mechanics. There are a couple of good ones out there. This is sort of the latest one I've got. It's really nice. And Statistical Mechanics is actually where physicists will kind of start from and sort of meet in the middle with thermodynamics. So these are going to, be, like I said, books 2 through 5, and I'll kind of I'll show you in each time where I'm jumping around. But honestly, I wanted to start off today, really just in basics. Come back here, is looking at first basic stuff within thermofluids. And the most important thing really here is that you have a thing called a system. I'm going to draw this as a piston, and the piston can kind of go up and down. There might be some valves letting air in and out of this piston. And what we're going to describe is the system might be sort of this stuff inside the walls and just above the piston. So as the piston is going up and down, the system itself is changing, which will make things interesting. And the system would be open if we're allowing mass to transfer in and out, or it would be closed when they say valves are shut. So a car engine like this going up and down and letting air in and fuel in and igniting, it's going to have, honestly, all of these features. So they're open and closed systems, right? And then, as like I said, as we get sort of into thermal fluids, we're going to look at this, and we're going to look at it from a fluid mechanics point of view, from a heat point of view, mass transfer, and honestly, we'll get to the point where we can solve these things. We can solve for how much power is this engine producing. And you really get into some of the more fun stuff. So thermodynamics is not a scary topic at all. And now there's fluid mechanics or heat transfer. And then honestly, like I want to finish just this little intro with why I believe in honestly like taking where you should have been as a student. Say if you're watching this as a junior and you're starting to take thermodynamics or fluid mechanics. Why am I going to encourage you to sort of embrace your mathematics and then maybe even level up? Well, just look at this example. So imagine here I have a block, and the block is floating on water. Okay? And I have some sort of atmospheric pressure above it. And then as you go down, the pressure as you go down, I'll call this distance y. This is water above you. That pressure is, what you're started with. And then plus the density of water times gravity times however far down you went. So honestly, if you're sitting at this point, you have this column of water above you, and it adds pressure. Have you ever done scuba diving, right? You literally can feel it in your ears because you have air inside. The air inside your cavity was probably from when you took a breath up here, and you're feeling it in the ears. Okay? And so you can look at this problem and say, as a buoyancy problem, if you know the mass m and you know its size and volume, then yes, you could solve for, if this is a straight thing on the side, you could solve because the pressure here on the bottom would be constant. It would be constant at that depth. And then the pressure here would be slowly decreasing, right? But it would balance out. And so maybe there's ways that you can simplify all of this and then you're okay. Well, gosh, what happens as soon as you don't have a box? Well, honestly, what happens is this. Now I've got an iceberg, or I've got some weird shape. Well, honestly, the physics behind this is I have a little, what we would call d area, a little infinitesimal piece of area with a normal pointing outward. That is at a depth of y. And so honestly, what the solution to that is the buoyancy force, I'll just call it capital B, is it's going to be the surface integral of P dA all around this body. And so let's keep that as y. Let's just define this as y for greater than 0. Like that's all that's happening. Okay? And so then if you continue and say, well, what's the pressure? Well, the pressure is the density of water times gravity times y, d area. Well, this is a contour integral. From your mathematical days, you actually know how to convert this to a volumetric integral through Stokes' theorem, where this then just becomes a volumetric integral, but you have to take the gradient, rho water, g, y, d volume. And again, this is for y greater than 0. Well, if you remember what that nabla is, I'll write it over here. That nabla is the derivative in the x direction, x hat, plus derivative in the y direction, y hat, plus a derivative in the z direction, z hat. Well, if I expand this through, I only have y here. I don't have x or c. And so then this is just the volume integral. Honestly, density of water and gravity pull out. The derivative of y with respect to y is 1. And so I'm left with this integral d volume for y greater than 0, and the direction it's acting is in the y hat. And there was a minus sign because pressure and the area were different. Okay, and so this was literally just the density of water times gravity times the submerged volume acting in the negative y hat direction, so upward. And you're done. You're done. That's buoyancy for you. And so all of this complicated mathematics, like none of this got any more complicated. And so, you know, we're going to see this over and over and over again, that a lot of times if we just keep things at the higher mathematical level, we do our manipulations at the higher mathematical level, we can cancel out so many things, and then, you know, turning the crank to get your answer, it becomes really, really easy. So, you know, hope you'll join me in this interesting book series. Like I said, book clubs sort of 2 through 5, which is thermodynamics, fluid mechanics, a little bit of graduate fluid mechanics, and a little bit of graduate thermodynamics, also known as statistical mechanics. And you, dear reader, follow along. Again, I'll hit the kind of the wave tops, and then you read along in the books as I sort of just do the wave tops and the reviews, and you will know the subject inside and out. Especially, remember, especially if you do the work at the end of, or you do those chapter examples and do the work in the book, you'll know this. See you next time.